Assembly Language Tutorial Chapter 7 Part 2. I hope you enjoyed the first part, and this is a continuation of the first part, so we'll jump on the second part. Arithmetic, integer arithmetic, this is part 2, and in this we'll talk about multiplication and division. There are 4 types of instructions here. Multiplication we do by invoking mul instruction, and for signed multiplication we use imul, and division we have the same. So what happens is kind of a tricky. I will show you the demo also and I will explain that, so I will get through the theory. So what we do is we store a certain value in the EAX register or the AX register or the AL register, and then we multiply it. Like you can see over here that there is only one operand. This is the opcode and this is the operand. So what's going to happen is whatever value is inside the EAX register, this BL guy is going to be multiplied into that, and the result would be stored in EAX. So what you see over here is like BL is like 8 bits, so it's 1 byte, but AX it's a 16 bit. So what's happening is after multiplication, the result would be stored into twice the size of what's being multiplied. Like if AL is there, so it would be stored in AX. If AX is there, it would be stored in EAX. What if the multiplication output is so big that it needs more space? So you run out of registers. So at that time you use this way, like you store the low bits in EAX and the high bits in EDX. So I've written it like a little kind of a explanation over there, so that's how it works. Now we have imul instruction as well, so multiplying the sign bits. So what we have a concept over there called sign extending. So you can go through that, so I have explained that. So if a value is like stored like -16, so the lower half, like 16 would be, let's see in the calculator, -16. So 16 is represented this way. So the lower half, the lower bits of lower half, so this is the lower bit FF0. So if you can see over here 1 2 3 4, so this the 1 would be the highest bit of the lower half, the 1. So the upper bit get filled with 1. It means this is like this guy over here, like the F over here. So suppose we are doing this multiplication EBX, so this EDX register would be filled with F. So we would see that demo. So otherwise this imul instruction is exactly like mul instruction. Everything is same. You can see that everything is same. So that's all about multiplication. And here is division. Do not worry, I will show you demo also, like what all these weird instructions mean. We'll see that in a debugger. So in division, as we see here, it's similar to multiplication, but what happened is we stored the remainder and the quotient into different places. Like if AX has the dividend, and now we are dividing it by BL, which is a divisor, so the quotient would be stored in AL and the remainder would be stored in AH. So that's what happens. So they divide by AX. So now as size increases, so what we see here is we store some of the parts in DX register and some of the parts in AX register as well. So the AX would contain the low byte and the DX would contain the high byte. So now we have, like, these are 16 bits, so it would be 2 bytes, and the AH and AL would each contain 1 byte, so 8 bits. So this way we can have a bigger number, and still we divide it by BX. So the quotient would be stored in, previously it was AL, now it is AX. So the same way. Now as you can see over here, AH and AL, they are part of one register, but here we are using 2 different registers. Same thing happens for this guy as well. We'll see that in the demo, and we will have more clarity. And here also we have a concept of sign extending, like taking out the bit of the most significant lower half, like we discussed over here. The highest bit of the lower half is 1, so you fill it with, take out the highest bit and store it into EDX. So we store them as F's. So here also similar thing happens, but this manual sign extension there, here it's happening automatically. We do not have to have another instruction, but here we do need. It's called CBW. So it sounds a little funky, but what it means is convert byte to word. So that's all that means. So here it would be convert word to D word, convert D word to quad word, that kind of stuff. Now IDIV and everything is same. Just do this, and rest all the things is exactly the same. Now demo time. I hope by now you would be getting comfortable in assembly programming, and this is an awesome tool, the Visual Studio IDE. So now we will talk about imul instruction. So here we have 4 and 4. So let's jump back to our slides. Now we are actually dealing with this part. So we have AX and BX. So we are here, the AX register, and then we are going to divide it by BX. So because it's a sign bit, so the product would be little funky, but I will explain them. So let's run this demo. Okay, so the AX register is 4, that is stored here exactly like that. BX is -4. EBX, as you can see, this guy, this is actually just the sign byte, the sign bit, whatever you want to call it. So FC. Now I will show you something that it's not 4 actually. So we are here, decimal. So if I store -4, let's see how it looks like. You know, FFFC. But if you do hex FFFC, it is something completely different. So how the computer knows that it's a negative number? Because of the sign bytes, this guy. So that's how it differentiates that it's a positive number, it's a negative number. I hope you already know that, just wanted to clarify that. So now we are going to multiply that. Now AX has the 4 and BX has -4, so after multiply it will be -16, and the result would be stored in AX. So let's see that. This is 4 FFF0. Let's see that. Let's open our calculator. Decimal -16 FFF0. Sure enough, that's what we have here. But if I do the backwards, FFF0, it is showed as 65,520 actually. So how the computer knows that? Because of the sign bits. And I will tell you one thing, like when you subtract or when you add something like -4 to 8, what happens? Let me show you that probably if you are not aware of. So I have a decimal over here like -4, which is this guy, FFFC. So as you can see right over there towards the binary thing, if you can see 1100, right, 1100. So it's -4. Now if I add it with 4, now let me write it here, you know, -4, it was written as 1100 plus sign bits, so we do not care about that much at this point. So now I'm going to add it with 8. So in hex 8 is 8, but in binary it is 111000. So 8 is actually 1000. So we see 4, right? We see 4. So now, like in decimal 4, if it is FFFC, like if it is FFFC, FFFC, which is 65,532 something. So it is stored as 1100. Something 1100. So now when you add this guy to this guy, let's see what we get. FFFC plus 8, we get 10100. So we get result equals 0100. So minus 4 is represented like this, 8 is represented like this. So what does this mean? 100. You see something? I hope you saw something. So you know what's happening, like all the negative integers are actually stored in a complementary way. Like if I show you again, actually that minus 4, when we talk about minus 4, it is actually stored as FFCC. But if you do this FFFC, it is actually 65,532. So when you add 65,532, so it is 65,532. Minus 4 is stored as like this, and 8 is stored as like this. So 8 is actually 8. So I'll remove it for simplification. When you do plus 8, so you get 65,540. So when you add, you get 65,535 plus 8, you get 65,540. And towards here in the binary you have like see the last bits, like 4 bits, 0100, 0100. We just saw that it's 4. Let's verify that. 100, it is 4. So this is what's happening. All the negative integers are stored in the memory in a complementary way. So that's what's happening. So just a quick refresher if you are not aware of that. So I think I should have cleared that out, and here I have done. So I hope that helps. So now the multiplication is done. Now we know that this is minus 4, and if you are like thinking something else completely and you have forgotten what we were doing, so go back to the video and come back here again. Now I'll continue. We'll talk about division instruction. Okay, so now we have minus 48 stored in AL register. Let's see what we have here. D0 is 208. So now you know that what's happening there. So in decimal it would be minus 48. So it is FF D0, but FF thing we haven't been reached there. And the next instruction, like the CBW, convert byte to word, it would take care of that. And sure enough, it took care of that, FFD0. So it's actually converting that into proper format. Had it not been done, if we would have divided, we would have got something completely different. Let's open the division slides for a bit. So what's supposed to happen is we are dividing AL by BL. So this guy over here, BL, which is a small one, the quotient would be stored in AL and the remainder would be stored in AH. So the quotient would be stored in lower byte. So here we will get the quotient. It means 48 divided by 5. What it is? So it is 5 cross 9 equals 45. So the quotient would be 9. So here we will get 9, and here we will get 45. 48 minus 45 is 3, so here we will get 3. So let's see that. Now we are going to divide. I step through it. So we got F7 and we got FD. So let's see what is FD in the calculator. Oh, I guess I messed up something. F7, right? F7, that is our 9, that is our quotient. Is it like minus 3? Yes, FD. So as you can see over here, our number, because when we divided minus 48 by 5, so what's going to happen is our all the divisions are actually in a negative number. So it's like dividing minus 48. So you will get 9 and minus 3, right? So what's going to happen is the 48 minus 48 part is going to become minus 9, right? Because just think of it, 48 divided by 5, what you get 9, right? 9 point something. So when you divide minus 48, you will get minus 9, right? And what would the remainder? Minus 48 divide minus 48 subtract. How you subtract? Minus 48 plus 45. So let me show you that. So it is minus 48 and then minus divided by 5, so you get quotient as minus 9, right? That we know, basic math. What you get a remainder is minus 3, right? So this guy over here, it's the low byte. The quotient would be stored in AL, which is the low byte, and this is AS, the high byte. So this would be the quotient. Now because all the sign bits are set, that's why it looks that way, even though we have been seen such cases like FF something, but these are like two different numbers stored in the register, so we have to think them separately. So minus 9 would be F7, that is stored here, and then minus 3 would be FD, that is also stored there. So I hope it makes sense, and watch this video a couple of times. This is sometimes it is cranky and confusing, I know that. So you have to like get yourself comfortable with running different programs, trying out on your own, and eventually it will make sense. And whenever you see any disassembled code in future, you will know what's going on there. Oh, I hope you enjoy the video, and I will catch you guys on the next one.